that it's conservative. Right there. If the partial of p, that means the partial of the first component with respect to y, is equal to the partial of q with respect to x, then you have a conservative vector field. I'll try and get to a proof of that as we move through this. I think for now, let's just take it and go with it. But I would box that. That's a huge deal, all right? We need that. Partial of p with respect to y must equal the partial of q with respect to x. I should also point out that this only works on two-dimensional vector fields. This is our check. So is this conservative or not? I give you a two-dimensional vector field. Is it conservative? So we have to check, right? We're checking to see, is the partial of p with respect to y equal to the partial of q with respect to x? Now, the first component function is p, and the second component function is q. So what is the partial of p with respect to y? 2x. Is that equal to the partial of q with respect to x? Yes, it is. Therefore, it is conservative vector field. All right? Which means that we have path independence. So if you give me any curve, right? Any curve, and you want me to calculate this, okay? Then we can do it, right? If you give me a curve on that vector field, I can calculate this with the fundamental theorem of line integrals. But what? How would you do that calculation? How would you use the fundamental theorem? What do we need? We would need an RT. Yeah, say I gave you that though. Say I gave you some curve. Okay, so we've got that. We've got the restrictions on this. This is all given to us. Okay, so I give you a curve. Okay, this vector field is conservative. We checked it. So if we want to do that, we do not have to go through all the computation of it. We need what?
We need f of xy such that the gradient of f of xy is equal to vector field.
That's right. Here, remember this with the fundamental theorem of line integrals says that we need to be able to evaluate the scalar function f at the two endpoints, right? But the scalar function f, right there, what is it? Right? What I can tell you is that this is conservative, so this is the gradient of some scalar function, but I don't know what that scalar function is yet. I have to go find it, don't I? I'd have to go find what the function, little function is that creates that vector field. We're going to do an example, all right? I'm just trying to get you to think ahead here. So this is me basically saying everything that I'm just said. Recall from 13.1 that f is conservative if there exists a scalar function such that the gradient of that scalar function is the field. In such a case, little f is called the potential function. So the potential function of the field is the scalar function. We now learn how we will find potential functions. We actually did this before. We got ahead of ourselves in the first section, and we actually did this thing with this partial integration. And I said we'd revisit it, and we're going to revisit it. Okay, so here's a field, right? First question, is it conservative? Second question, if it is conservative, find its potential function. In other words, find little f then. So first, the check for conservative. Well, I need partial of p with respect to y to be equal to the partial of q with respect to x. Is that true? So this is p, this is q. So what is the partial of p with respect to y? 2x. What is the partial of q with respect to x? 2x. 2x, beautiful. This is conservative, isn't it? We have a conservative vector field. Now, that means that this is the gradient of something. We have to go find it now. Therefore, f is equal to the gradient of some scalar function, which is partial of little f with respect to x, partial of f with respect to y. That's what it meant to be the gradient vector field. You took the partial. So that means that this p right here is this, right? And the q is this. So do you all remember how I started this out when we were trying to go backwards? I write down, so, all right, this must be 1 plus 2xy plus natural log x. Then what did I do? I'm trying to get back to little f. Integrated with respect to x. Okay, so we do the antiderivative of this with respect to x. Antiderivative of this with respect to x. The left side becomes little f, right? So look, we are starting to get a formula for the potential function. Here it is. This is what we know about little f so far. It is equal to antiderivative of that with respect to x plus antiderivative of that with respect to x. X squared y. And the grand finale, the antiderivative of the natural log of x. That's the derivative of it.
It's like really long, isn't it? It's like 1/2 ln.
It's not super long. It's that x ln x minus x. So that may not be something you know off the top of your head, but that is, you can get that in Cal 2 by doing integration by parts. You just do like u is equal to natural log x, dv is dx, and then this again is how you were taught. This all depends on how you were taught. You pick your u, your dv, then you go like here and then go back up, v is x, and then ultraviolet minus integral voodoo, I mean all that stuff, and it'll work out. This all becomes this. That's how it's done. All right, now, very important, this part. What am I missing?
Oh yeah, plus c, which is our plus.
Yeah, this thing can have y's in it also. So we said like h of y, h of y. So instead of a constant of integration, we have a function of integration that has, at the most, that h can have y's and numbers. That's it. Can't have any x's mixed in with it. Okay, then what did we do? We know f up to some function of h. We don't know what this is yet. So how do we go after that? We take the partial of this with respect to y and try and get it to match up to that, because that's the partial of f with respect to y. So now taking the partial of that with respect to y, we get this. From here, partial of f with respect to y must be 0, right? Plus x squared, right? Partial of that with respect to y is just x squared. Plus, what's the derivative of all this stuff? Zeros, because these are all constants. And then what's the partial of h with respect to y? H prime y? I'm going to write it this way. That's the same thing as the partial of h with respect to y, right? But that has to match this, right? Right? Wait. Where did I get what? Sure? Milton, what were you fanning around in here today? What was that? Did you release a gas in here for us?
Okay,
We're all
serious. We found this out yesterday in physics. Apparently, okay, and like it's not so long. It's not like the actual STD. There was chlamydia on the hand dryers, and I used the hand dryer, and I was like, I don't know if this chlamydia can like cause like, like sneezing or like fever or something like that. So like, I used hand sanitizer, but my hands were still wet because I like washed them. And so like I was like banding them, so like the hand sanitizer.
So if we all get pink eye this weekend, we'll know.
I
Thanks,
washed my hands,
Milton.
so I just didn't care, like, using water.
That's kind of gross.
My teacher told me that. I didn't.
All right, so we're good? We're good? All right, so we need this to match. We need this to match up with what the partial of f with respect to y is supposed to be, which is x squared. And what does that mean? The partial of h with respect to y is 0, right? Which means if we integrate this with respect to y, then what does that mean that h had to be? Just a constant, just some constant that we don't know. So h must be a constant. And you could put h of y if you want. H of y is just some constant that I don't know. So do we have a formula for little f now? We do, right? We have a formula for little f. Little f, the potential function is x plus x squared y plus x ln x minus x plus some constant, right? And I just realized here that those x's cancel. So we get x squared y plus x natural log x plus a constant. Any constant we want, okay? Any constant we want. So that we could use 0 and then it would be nice and clean, could we? Questions? Check that it's conservative. Since it is, go find its potential function using this thing called partial integration. I believe the next example is going to kind of bring it all together. Let's see. There we go. It does. Whoa, what did I do? If f is equal to that vector field, what I'd like for you to do right now, just take a deep breath. Well, I wouldn't take deep breaths right now. He'll be here. Milton, I hope you don't mind. You're not getting offended that I'm picking on you.
Well, it just brings me back to like my old high school.
So this is not new to you. Is that what you're saying?
Honestly, not at all. Like, I'm used to this. I thought it was going to be different, but I guess not.
No, it's not. Okay, so try and just kind of like clear your mind. Let's say we started this problem. Let's say we started this problem at the beginning of class today. All right? Then the approach to this would be, I give you a vector field, I give you a path, I give you the time constraint or t constraints, and I ask you to calculate work, right? So you're going to go through the standard protocol. You're going to go and find the derivative of this, put it there. You're going to get the vector field, but you're going to evaluate it at this, right? So every x gets replaced with that, right? All your y's get replaced with that, and then you dot those, and then you integrate. And that would be a real pain, wouldn't it? Yep. Now let's just open our minds up a little more to what we just have learned. We look at this and we say, well, wait a minute. That would be a lot of work to do, right? So maybe it's conservative. Maybe this is a conservative vector field. If it's conservative, then all I would have to do to calculate this would be to evaluate the potential function, little f, at the two endpoints of this curve, which should be easy to get because I have the two time constraints, so I could plug in 1 and plug in 2. I'd have my two endpoints, right? So I just need to know if it's conservative. So we go check, is it conservative? We did that. That's the previous example, right? Then we go find its potential function. We just did that. So we've got this all set up now, right? Now we had to do some work for it, but it's still, I think, better than doing the original, which was trying to dot all that stuff together. So what was my potential function? I've forgotten now.
X squared y
X squared y
plus XL and X.
plus XL and X. And then plus C, right?
Yes, sir.
Now for C, I'm just going to use 0. Because that is a potential function, right? That'll qualify, that works. All right. All I have to do now to get an answer to this is evaluate this at the two endpoints. So let's go find my endpoints. So what is R of B for us? And what is R of A? So you need to know what A and B are. R of B is R of 2 and R of 1, right? So we're going to plug 2 into this and then plug 1 into this. So what do we get? It's a vector. What do we get here?
Five, four.
5, 4, thank you. And 1, 2, 3. Y'all know what I'm doing, right? Yeah?
Yes.
This is A, this is B, this is R. I plug in B, I plug in A, there they are. And now I'm going to get to the answer. The line integral over C, f dot dr should be equal to my little scalar function evaluated at R of B minus my little scalar function evaluated at R of A, which for us is our little scalar function evaluated at B, which is the vector 5, 4, and then minus our little scalar function evaluated at A, which is our little vector 2, 3. And then now you just replace x and y into the little scalar function, and we should be in business. So let's try and do this. 5 goes in for x, 4 goes in for y. So 5 here, 25, right? Times 4, so 100. Minus, or plus, sorry, I don't know why I said minus. Plus what?
We're plugging this into the little f, right?
Little f, yep, little f, the potential. 5 ln 5. And then subtract from that whatever I get when I plug in 2 for x and 3 for y. So 2 for x, so 2 squares 4, and then 3, so 4, 12. 12, and then plus 2 ln 2. Which would be 88 plus, sorry?
Plus the 5 on 5
Mm-hmm.
minus 2.
Yep. What did I do there? Properties of logs. This 5 can go up 5 to the 5th, natural log 5 to the 5th. This is a natural log of 2 to the 2. And then because this is a minus, you'll have subtraction between two logs and turn that to division in one log. So there you go. So yes, you do have to check that it's conservative. I understand that takes a little bit of work. And then you have to find the potential function, little f, which is that partial integration. Yes, I understand that's a little work. But I assure you that it is far cleaner than what it would have been for us to have to put that all together and do what we did at the beginning of class. Okay, we are moving on. This is a great theorem. I mean, a great result. This fundamental, well, it is a theorem, fundamental theorem of line integrals. But we have avoided three-dimensional vector fields on purpose. So we have not seen what it takes to show that a vector field in R3 is conservative, but we can still use partial integration to try to see if a potential function exists. Later on, there will be a check for conservative vector fields three-dimensional. There will be a way to check it. Just not yet. So is this, should that say is? Maybe that should say is. No. Does that make any sense? Yeah, okay. Yeah. So here we go. Go ahead. Yep.
We can always find a potential function, right? Like
can't always.
So if we can, then we know it's conservative?
But it's not an efficient way of checking. There's a more efficient way of checking. If all we needed to know is whether or not it was conservative or not, we would like to have a fast way of doing it. If it's a two-dimensional vector field, we have a fast way. Partial of p with respect to y has to be equal to the partial of q with respect to x. Now, if we're doing a line integral, we have to go find little f anyway, so we have to do integration, partial integration. But three-dimensional vector fields, we don't have the quick check yet. But we can still go see, maybe it does have a potential function. Do you remember last class, I gave you an example of one that was not conservative, and we went and tried to find the potential function? We got a contradiction. We said like our function h can only be a function of y, but then at the end we said that h had to have x in it also. So it, like, yeah, no, there was a problem there. All right, here we go. So find the potential function. So we are assuming, right now we're going to assume, so suppose that this is the gradient of some scalar function. That's my suppose symbol, right? Not mine, that's mathematical suppose symbol. Suppose that this vector field is the gradient of some scalar field, which if it is, then that means it's a vector that has the partial of f with respect to x, partial of f with respect to y, but now this new partial of f with respect to z. So that means this would be that, right? This would be that, and this would be this. If it is conservative, that's what would have to be true, right? So let's start off like we did the last one. Let's write down partial of f with respect to x would have to be 2xz plus y squared. And then let's try and recover what little f is. So how do we do it? Integrate that with respect to x, because we're trying to undo the partial with respect to x. So we integrate it with respect to x. All right, left side is what? Just the left, okay, and the right side is x squared z plus xy squared Yeah, so whatever's here could be a constant. It could have y's in it, right? But it could also have z's in it. Do you all agree with that? Because if it has y's and z's in numbers, when I take the derivative with respect to x, it'll go away. But it could have all of those, constants, y's, and z's. So I'm not going to say that this is h of y. I'm going to say it's h of yz. It's actually, it is potentially a function of two variables as opposed to one. All right. Now, let's play the game again. Let's take the derivative of that with respect to what this time? Y. So we take the derivative of that with respect to y. So the partial of that with respect to y would be, let's see here, 0, right? Here, 2xy, and then plus, what's the partial of this with respect to y? I don't actually have no idea what it is, but I'll call it the partial of h with respect to y, right? Okay, what does that have to match? What does that have to match in order for all this to work?
The partial y or something like that.
Yeah, it has to match this, doesn't it? Okay, so I have that 2xy plus partial of h with respect to y must equal, hey, 2xy. What does that mean? Partial of h with respect to y must be 0. And what does that tell me? This is a critical point right now. that there's no y's in it. Okay.
What couldn't it still be like, y times z and we have a z? Like, when we took when we integrated with respect to y, and we just said it was h and y, or couldn't it still have like a y times z or something?
You could have some z's in here still, right?
So then what?
So what we need to do now is say, I want to get what h is. I would really like to know what this is, wouldn't I? Like if I had that, I'm done. But here's the most I can say about it. When you take the partial of this with respect to y, you get 0.
Yeah.
Okay? So if I integrate this right now with respect to y, integrate 0 with respect to y, I know this side is h, right?
Yeah.
This side is constant, or could have a z in it. Could have a z in it. So this is some function of z. I'll call it g of z. So here's what I've been able to establish. This h function that I said could potentially have y's and z's in it, so far what I know is that it doesn't have y's in it. It just has, at the most, z's and maybe some constants. Okay. Now what?
So,
Let's go back to this. Let's go back to this and let's rewrite it.
call it h. Yeah.
And let's replace h with what we know about h, which is, what do we know about h?
There's no y.
And there's no y in it, so it is strictly a function of z. And now let's do a derivative of that with respect to z. So what is the partial of that with respect to z? X squared plus,
X, y squared.
yeah, so that's going to go away, right?
0,
So then we have what? Plus partial of g with respect to z. Right? But we need this to match to that, don't we? So we have that x squared plus partial of g with respect to z must equal x squared plus 3z squared. And these x squareds cancel, and that means the partial of g with respect to z must be 3z squared. And remember, all I needed to know was what g was, right? And I think I'm going to be able to figure it out because I know the partial of g with respect to z is this. So if I integrate this with respect to z, integrate that with respect to z, then this side will be g, right? And this side will be z cubed plus a constant. But I know there's no y's in it, right? It's just a constant at the most. So I think we're there. We have our candidate for little f is x squared z plus xy squared plus g of z, which we believe to be z cubed plus a constant. Now that constant could be any constant. I don't care about which constant is. Let's just make it 0. So there it is. We believe that this is the what function? Potential function. And we can check it, can't we? You can just check it real quick to see if you got it. Take the partial with respect to x. 2xz plus y squared. Okay, take the partial with respect to y. 2xy. Take the partial of this with respect to z. X squared plus 3z squared. There you go. So this is the potential function. A little more complicated when you have that other additional variable in there. Yes?
Let's say I was solving this. Could I have gone to the f of z first rather than
Yes.
the f of y?
Yes. You could start at anything. I just started, let's go with x first. If you want to, you could say, okay, partial of f with respect to z has to be that last one. Integrate with respect to z. Then you know that you got, instead of a plus a constant, you would have some function of x and y, potentially. And then you differentiate that with respect to either x or y. It's up to you. Yeah, you have some freedom.
Would there be times where it makes sense to do other variables first?
I don't, in the problems that I've ever seen with these, maybe it would have been easier to start with the other one, but I've always looked at it as if it's going to work, it's going to work, like, or it's not going to work. Yay. We're at the end. Right? That was it. Yes. Uh-huh.
Was middle one with the partial of little f with respect to y, and you took the integral of h sub y and 0, and you only said g of z is because you knew that the z function had something like extra on, like, I don't know how to phrase this, like, how come you didn't add a c there?
Oh, because it's included in this. This function itself could have a constant in it. But I'm also saying that it could have z's in it.
Okay.
See, if I just say plus c, then you're ruling out z being there.
Okay, so that includes all.
Yeah, this can be any function of z, including just constant itself.
Okay.
Yeah.
Could they have both been 0? Or
Yes.
Yeah.
Yep. You could have, you mean like this one come down and we would have found out that this partial would have been 0?
Yeah.
And then come back and said it's a constant? Sure. Actually, that's what I thought it was going to happen, but it didn't happen here for this one. All right, so yeah. I think that's probably a good place to stop. Let me see what the next section is. Oh, Green's theorem. This is the first tattoo I ever got in my life.
What?
Was this tattoo, yeah. I have some mathematical tattoos. Yeah, I don't regret Green's theorem. I really do like the...
Is it on your lower boxer?
Huh? Yeah, it's right here. It's right here. I've got flowers around it too. No, I didn't do the whole theorem. It was too much. I just put the first part of it. Okay, so sneak peek. I'll let y'all go. Don't worry, I'll let you go. But from here on out, we have some major results in this chapter. And Green's theorem is the first big one. And I just want to show it to you real quick. This is a line integral. I know it looks messy, but this is a line integral. In fact, I should point this out. Maybe you're not getting out of here until time. Okay. This is work, right? That's work? That's work? Okay, that's just the notation expanded out a little bit. If R of t is some function of x, or some x function of t, and the y is some function of t, then what does this become? In other words, if I have my vector curve and I've got these two functions in here, then, and let's also say that f is some p and some q. Okay, so I've got a vector field with two components and I've got my path. Then this becomes what? What is this? Tell me that first.
X minus t and y prime.
That's x prime t. So you're basically taking derivative of that, right? X prime t, y prime t. And that's in a vector. And you're dotting that with p
P of x.
with that plugged in and q with that plugged in, right? So p with x of t plugged in, and then q with x of t plugged in. I know that's getting messy. But then you dot them, right? There's a what?
Y.
I'd put, yeah, y of t, sorry. And now if I dot them, I get integral, I get p of x of t with that, plus q of y of t with y prime of t. And do you all see that this is the line integral with respect to x and the line integral with respect to y? That's basically this expression right here. Okay? I stretched out pretty quick and I did that fast and sloppy, but can you believe me when I say this is work? This is basically the work integral, all right? What we're going to find with Green's theorem is that if you're trying to take a path, all right, and trying to calculate work on it, we have this new theorem that says if the path is closed, okay, if the path is closed, and forget conservative, throw all that out the window right now. Forget the conservative. If you have a closed path and you want to know the work along this path, you can actually do a double integral of this region. So instead of having to worry about going around the path, somehow you can do a double integral over a region. So we're going to be able to do work, calculate work using double integrals, which means we may go back to polar coordinates, we may go back to type 1, type 2 regions, but it is a way of connecting line integrals and double integrals together. We'll see. We're going to do these, but pardon?
The circle on the integral?
Okay, so this circle on the integral is telling everyone that the path you're traveling over has to be closed.
Oh, okay.
So you know how I said, like, if we want to do work there, we've got to just do it. We've got to go calculate it. But if our path is closed, then this theorem holds. So that is to assure you that it is a closed path. All right, we'll start that next week. We have Green's theorem. All we have left, it sounds like not much. Green's theorem, curl and divergence, parametric surfaces, surface integrals, and the grand finale, the two theorems, Stokes' theorem and divergence theorem. Just 6 more sections and 6 more class meetings.
And it matters what direction?
It matters which direction. Yes, it will. And the way we'll do it is we'll imagine you were standing here walking along this curve. What you want is that the area region is to your left as you're walking. That's the standard direction. What gets problematic is there's an extension of this in a 3-dimensional space. So then your orientation matters a little more, because can you imagine that's like a curve, closed curve in 3-dimensional space, and this surface between them, right? Imagine walking, you could be standing here, walking around like this, and then it would be like this. But you could also be like standing upside down, right? Walking along like that. So we have to have like an agreed upon orientation of things. That's going to be Stokes' theorem right here. Stokes' theorem is basically Green's theorem, but we break out into 3-dimensional space. Okay, have a good weekend. Have a good holiday. Friday is a holiday, so campus is closed. I won't be here, and you shouldn't either. Pardon? They're sanitizing everything, I think, this Friday is what they told me.